In this recording, I'd like to talk about the Borel-Cantelli lemma. So let's get started. All right, so I want to talk about the Borel-Cantelli lemma. Before we do that, we need to define a certain quantity here, written in purple, lim sup of an. So let's see what's going on here. So suppose omega fp is a probability space, and suppose n going from 1 to infinity is a subset of f. In other words, n going from 1 to infinity is a sequence of events. So we're going to define the event lim sup an as follows. So lim sup an is defined to be the intersection n going from 1 to infinity of the union k going from n to infinity of ak. In other words, here's what we're doing. For each n, we look at the union k going from n to infinity, ak. Now, this is something that, of course, only depends on n. Perhaps you could call it bn. And then what we're doing is we're taking the intersection of all such bn's, n going from 1 to infinity. And whatever it is that we get, that's what we're taking as a definition of lim sup an. All right, so that's what we have. Lim sup an is defined to be the intersection n going from 1 to infinity, union k going from n to infinity of ak. Now, the Borel-Cantelli lemma is going to be a lemma which tells you that under such and such conditions, the probability of lim sup an is 0. And there'll be another part of the lemma which says that under such and such conditions, the probability of lim sup an has to be 1. But before we get to that, let's just talk about what this event represents in words. So let me first write down what this event represents in words, and then I hope to convince you that this mathematically does in fact correspond to what I'm writing down in words. So here's what I claim. So in words, lim sup an consists precisely of those omega in omega which belong to infinitely many of the ANs. As an example, if there is an omega which belongs to A1, A4, A7, A10, A13, A16, and so on, then such an omega will be in the lim sup. Similarly, if there's an omega which belongs to A10, A20, A30, A40, ... then such an omega will belong to the lim sup. However, if I have an omega which belongs to A1, A2, A5, A8, but doesn't belong to any A's after that, then such an omega will not be in the lim sup. But anyway, let's make sure we can understand this from the mathematical definition. So I claim that lim sup an consists precisely of those omega and omega which belong to infinitely many ANs. So let's see why this is true. So indeed, omega is in lim sup an if and only if omega belongs to this quantity. Now, if omega has to belong to the intersection n going from 1 to infinity of these guys, that means for every n, omega has to belong to the union k going from n to infinity ak. Right? So omega is in lim sup an if and only if for every n greater than or equal to 1, omega belongs to the union k going from n to infinity ak. This is simply using the basic idea that a point belongs to the intersection of a family of sets if and only if it belongs to each of them. All right, now let's go one step further. Now let's look at this. So for every n greater than or equal to 1, omega must belong to the union k going from n to infinity ak. Well, if omega has to belong to a union of all these guys, that means omega has to be in at least one of them. So what we get is, if and only if for every n greater than or equal to 1, there exists k greater than or equal to n such that omega is in AK. All right. So omega is in lim sup an if and only if omega is in this quantity that I'm underlining. This quantity is the intersection of these unions. So omega is in lim sup an if and only if for every n greater than or equal to 1, omega is in the union ak going from n to infinity. Now omega is in this union if and only if it belongs to at least one of the AKs. So putting the pieces together, omega is in lim sup an if and only if for every n greater than or equal to 1, there exists some k greater than or equal to n such that omega belongs to ak. So one way to interpret this is saying no matter how far you go into the sequence, and that is captured by the number n, somewhere further along the line, namely for some k greater than or equal to n, omega falls in the set ak. If you think about it, this is precisely a mathematical way of saying that omega belongs to infinitely many ans. Okay, so we've convinced ourselves that lim sup consists precisely of those omega and omega which belong to infinitely many ans. All right, now let's see what the Borel-Cantelli lemma says. All right, so here's our theorem. This is the Borel-Cantelli lemma. This thing has two parts. Okay, so let's see. So suppose omega fp is a probability space, and let n going from 1 to infinity, subset of f, be a sequence of events. Okay, so the first part of the Borel-Cantelli lemma says the following. If some n going from 1 to infinity, p of an is finite, then p of the lim sup of an must be 0. All right, let's see what the second part says. So let's just play a bit. The second part is going to say if the sum n going from 1 to infinity, p of an is infinity, and in addition the events a1, a2, dot, dot, dot are independent, then you can be sure that p of lim sup an equals 1. Okay, so let's see why this is true. So let's prove this. So let's start by proving 1. So remember that lim sup an, this is by definition the intersection n going from 1 to infinity, the union k going from n to infinity ak. Now, I'm taking the intersection n going from 1 to infinity of these guys. In other words, the intersection is going to belong to any one of these no matter what n I take. Okay, so this is going to be a subset of the union k going from capital N to infinity ak for any natural number n. Right? What I'm saying is that the intersection n going from 1 to infinity of these unions, the intersection of these sets is a subset of each of these sets. In particular, the intersection of these sets is a subset of the union k going from n to infinity ak for any n greater than or equal to 1. All right, so now what I'll do is the following. So probability of lim sup an is going to be, now I'll say that lim sup an is a subset of this union. And now I'll use countable subadditivity. And so I'll say that probability of lim sup an is less than or equal to the probability of the union k going from capital N to infinity ak. Actually, I said I'm using countable subadditivity here. That is not true. I will now use countable subadditivity. What I just used was monotonicity. Namely, bigger sets cannot have smaller measure. Okay, so far I've used monotonicity. So P of lim sup an is less than or equal to P of the union k going from n to t, and say probability of this countable union must be less than or equal to the sum of the probabilities. So this is less than or equal to the sum k going from n to infinity P of ak. And now I claim that this thing goes to 0 as capital N goes to infinity. Let's see why this is true. Why? Here's why. If an is greater than or equal to 0 and sum n going from 1 to infinity an is finite, then the sum n going from capital N to infinity an goes to 0 as capital N goes to infinity. So this is a fact you study when you study convergence of series in real analysis, right? I have a sequence AN which is greater than or equal to 0. So I'm taking a series with non-negative terms. Suppose I have some n going from 1 to infinity AN, and suppose that series is convergent. Remember, I'm taking AN greater than or equal to 0. Then I can be sure that the sum of the tail vanishes. What do I mean by the sum of the tail? I mean, I take the sum of AN starting from some point capital N all the way up to infinity. So if I take this tail, which is the sum of n going from capital N to infinity, as capital N gets larger, this tail goes to 0. So you're familiar with this fact from convergence of series, and that's all that I've used here. So I've said that since the sum n going from 1 to infinity P of AN is finite, the sum k going from n to infinity P of AK must go to 0 as n goes to infinity. So this is since sum n going from 1 to infinity P of AN is finite. All right, so what do I have? I have, let me just write it down once again. P of lim sup AN is less than or equal to the sum k going from n to infinity, P of AK, right? Now this thing is true for every n. If it's true for every n, then I can take the limit as n goes to infinity on both sides. Remember, the left side is independent of n, and now the limit as n goes to infinity, sum k going from n to infinity P of AK is simply 0, as we have noted, and so P of lim sup AN is indeed 0. All right, so that is the first part of the Borel-Cantelli lemma. It says that if the sum n going from 1 to infinity P of AN is finite, then P of lim sup AN must be 0. No other assumptions were put on the family of sets A, and the only assumption put was that the sum n going from 1 to infinity P of AN must be finite. All right, now let's get to the second part. And here I want you to note that here, of course, we're having sum n going from 1 to infinity P of AN equals infinity, but we're also putting this restriction that A1, A2, and so on should be independent. Anyway, let's see how you'll prove the second part of the Borel-Cantelli lemma. So let me just start with a fact. This is a fact that we'll use in the Borel-Cantelli lemma. So this fact I'm stating is really about calculus or real analysis, however you want to think of it. So here's a fact. So for any x greater than or equal to 0, we have 1 minus x is less than or equal to e to the negative x. All right, let's check this. Why is this true? All right, so here's why. Let's say I look at e to the negative x minus 1. I realize that this is e to the negative x minus e to the 0. And then using the fundamental theorem of calculus, I say, well, this is simply the integral from 0 to x minus e to the minus s ds. Okay, I've simply used the fundamental theorem of calculus. Now I'll say, remember here I'm taking x greater than or equal to 0. So this upper limit of integration x is greater than or equal to 0. And of course, s is going between 0 and x. So in particular, s is greater than or equal to 0. So for s greater than or equal to 0, we have e to the minus s is less than or equal to 1. So for s greater than or equal to 0, we have minus e to the minus s is greater than or equal to minus 1. And now I'll integrate both sides. Or put another way, I will say e to the minus x, e to the minus x minus 1 was integral 0 to x minus e to the minus s ds. But minus e to the minus s is greater than or equal to negative 1. So e to the minus x minus 1, which is what I have here, which equals this integral. And now what I'm saying is that since this integrand is greater than or equal to minus 1, I'll get this is greater than or equal to integral 0 to x minus 1 ds. And of course, on the right side, I'm simply going to get minus x. And when I rearrange this, I'm going to get 1 minus, I'll take the 1 to the other side, so I'll get 1 minus x is less than or equal to e to the negative x. All right, so this proves the claim that we just made. This proves this fact about real numbers. Anyway, this is something that we will use in the proof of the second part of the Borel-Cantelli lemma. All right. So we have this under our belt. Let's go back, see what Borel-Cantelli says. It says, suppose the events A1, A2, and so on are independent, and the sum n going from 1 to infinity, P of an is infinity, then P of lim sup an has to be 1. All right, so let's see how we'll prove this. So we want to show that probability of lim sup an is 1. In other words, we want to show that probability of the intersection n going from 1 to infinity union k going from n to infinity ak is 1. Now, of course, if you want to show that the probability of some set is 1, it is just as good to show that the probability of the complement of that set is 0. i.e., we want to show that the probability of intersection n going from 1 to infinity union k going from n to infinity ak complement is 0. All right, now let's see what this operation of taking complements does. Here's where we'll use De Morgan's laws. That is, we want to show the probability of, so now I'll use De Morgan's laws. So complement of the intersection is the union of complements. So this is going to be union n going from 1 to infinity of the complements. So I have union k going from n to infinity ak complement. Okay, so far I've just used De Morgan's laws. I've said probability. So basically I've said that the complement of the intersection is the union of the complements. Now I'll use De Morgan's laws once again. Okay, I want to show that this is 0. i.e., I want to show union n going from 1 to infinity. And now again, I'll use De Morgan's laws and I'll say complement of the union is the intersection of the complements. So I'll intersection k going from n to infinity, ak complement is 0. All right, so this is what we want to show. Let me go ahead and give this a name. So star is what we want to show. If we show star, then we're done. Now let's see how we prove star. All right, so if we prove star, then we're done. So let's see how we'll go about doing this. So okay, and let some natural number greater than or equal to n. And now what I'm going to do is I will consider the probability of intersection k going from n to m of ak complement. Remember, we've talked about independence, and in undergraduate probability, you talk about independence of events. And now we talk about independence of sigma algebras. I'll leave it to you to check. Remember, if we say that the events A1, A2, dot, dot, dot are independent, what that's saying is that the sigma algebra A1, which consists of the empty set A1, A1 complement omega, the sigma algebra A2, which consists of the empty set A2, A2 complement omega, the sigma algebra A3, dot, 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 all these sigma algebras are independent. And so I'll leave it to you to check that the probability of the intersection of these guys is going to be the product of the probabilities. All right. So by independence, what I'm going to have is probability of the intersection k going from n to m, ak complement. Actually, let me take this to the next line. Okay. Probability of the intersection k going from n to m, ak complement. By independence, this is going to be the product of the probability. So this is product k going from n to m, p of ak complement. Okay, so here I've simply used independence. And now I'll say that the probability of the complement of a set is just 1 minus the probability of that set. So I'll get, this is product k going from n to m, 1 minus p of ak. All right, and now we'll use this fact from calculus or real analysis that we had. What did the fact tell us? The fact told us that 1 minus x was less than or equal to e to the negative x whenever x is greater than or equal to 0. And so we'll use this with the role of x being played by p of ak. So this is going to be less than or equal to product k going from n to m, e to the minus p of ak. Okay, this is simply using the fact we had on the previous page. And what is this thing? Now I'll say that I'm taking a product of e to the something. So when I'm taking the product of e to the something, I'm going to get e to the summation of the exponents. So I'm going to get e to the minus sum k going from n to m, p of ak. All right. Okay, so what do I have? I have p of intersection k going from n to m, ak complement, is less than or equal to e to the minus summation k going from n to m, p of ak. So far, I haven't done anything clever. I've just summarized the previous line. That's all. Now, remember, what I'm interested in is infinite intersections and all. So let's look at p of the intersection k going from n to infinity, ak complement. Now, I claim that this is going to be the limit as m goes to infinity, p of intersection k going from n to m, ak complement. Let's just see why this is true. So let Gm be the intersection k going from n to m, ak complement. All right. So what is Gm plus 1? Gm plus 1 is the intersection k going from n to m plus 1, ak complement. In other words, as m gets bigger, you're taking intersections of more and more sets. And you know that as you take intersections of more sets, the result can only get smaller. So what you have is you have that Gm has to contain Gm plus 1. In other words, what you have here is you have a decreasing sequence of sets. And you remember that for a decreasing sequence of sets, you have continuity from above, right? Probability of the intersection is the limit of probabilities. So what you have is limit m going to infinity p of Gm. Right? And what is the intersection of Gm? Oh, maybe this should start at m equals n to infinity. I'm sorry, it should not start at 1. So intersection m going from n to infinity Gm. This is simply the intersection k going from n to infinity ak complement. All right, so that's what I'm using here. probability of the intersection k going from n to infinity, a k complement is the limit as m goes to infinity, p of intersection k going from n to m, a k complement. So basically I'm saying, think of this as my gm. This thing is only defined for m greater than or equal to n. Now, as m gets bigger, I'm taking an intersection of more and more sets, so the result keeps getting smaller. And I know, so the result is I get a decreasing sequence of sets. So I have Gn, which contains Gn plus 1, which contains Gn plus 2, and so on. Uh, right? And so what I know is that the probability of the intersection is the limit of the probabilities. And so that's exactly what I'm using over here. Okay, so probability of the intersection k going from n to infinity a k complement is the limit m going to infinity p of intersection k going from n to m a k complement. But wait a second, this quantity, we have an upper bound for this. The upper bound for it is this exponential thingy, right? So by the previous line, this is going to be less than or equal to limit as m goes to infinity of this exponential thing, k going from n to m p of a k. And now wait a minute once again. Here I'm taking the limit m goes to infinity of e to the something. Okay, let me rephrase that. I'm taking limit as m goes to infinity e to the minus something. Now, as m goes to infinity, that something goes to infinity. In other words, as m goes to infinity, I basically get something that looks like e to the minus infinity, which is, of course, 0. And so this limit is 0. All right. So what do you get from this? You get that for any n, probability of the intersection k going from n to infinity a k complement is 0. Put another way, thus for any n greater than or equal to 1, intersection k going from n to infinity a k complement is a null set. Remember, a null set is a set with measure 0, in this case with probability 0. But wait, if I have a countable collection of null sets and I put them together, I will still have a null set. So, right, so for each n, this guy is a null set. So if I take the union of all such guys over all n's, I will still have a null set. So union n going from 1 to infinity, intersection k going from n to infinity, a k complement is a null set. In other words, probability of the union k going from 1, no, let me not use k. A union n going from 1 to infinity, intersection k going from n to infinity, a k complement is 0. But wait a second, this is exactly what we wanted to show. We wanted to show that probability of the union n going from 1 to infinity, intersection k going from n to infinity, a k complement is 0, and that's exactly what we have. Probability of the union n going from 1 to infinity, intersection k going from n to infinity, a k complement is 0. And so we're done. And this completes the proof. All right, so that completes the proof of the Borel-Cantelli lemma. All right, so it has two parts. Now, the next thing I want to mention is I want to make this a tutorial problem. Whether or not it's written up in a tutorial, I'm expecting that you will do this as a tutorial problem. So here is a tutorial problem. Instead of a probability space, I will take a measure space. Remember, every probability space is a special case of a measure space, but not the other way around. So suppose omega f mu is a measure space. And suppose I have a and n going from 1 to infinity, which is a subset of f. In other words, I have a sequence of measurable sets. As before, lim sup an is defined in the same way. It's the intersection n going from 1 to infinity, union k going from n to infinity, ak. Now, the tutorial problem asks you to prove the first part of the Borel-Cantelli lemma. That is, Namely, show that if the sum n going from 1 to infinity of mu of an is finite, then mu of lim sup an is 0. Okay, so the tutorial problem is to show in an arbitrary measure space that the first part of the Borel-Cantelli lemma holds. And here's just a question for you to think about. Is the second part of Borel-Cantelli meaningful in an arbitrary measure space? Basically, what I'm trying to hint at is that the first part of the Borel-Cantelli is a purely analytic statement, whereas the second part is a certain probabilistic statement. And so I'm basically hinting that the answer to the second question is not quite. I don't want to say outright no, but the answer to the second question is no. The second part of the Borel-Cantelli lemma involves independence. Independence is a concept you don't see in real analysis, something you see in probability. That's one of the things that's there in probability that you don't see in analysis. The second part of Borel-Cantelli does use independence, which is an inherently probabilistic concept. I'm not sure it has any direct counterpart in analysis. Whereas the first part of Borel-Cantelli is basically a result of real analysis. So the first part of Borel-Cantelli will be true even in an arbitrary measure space.